Okay.
So today's guest lecture is by John Meriwether, Dr. Professor John Meriwether, and he's well known in our community on his work with the upper atmospheric dynamics, and particularly I always associate when I see John Meriwether, I associate him with étalons and Fabry-Pérot interferometers, uh, and he's currently a research professor at New Jersey Institute of Technology, and he's contributed for decades and decades to experimental aeronomy and ground-based optical diagnostics of the thermosphere. He's earned his bachelor's degree from MIT in 1964. That's a while ago, and his PhD from University of Maryland, College Park in 1970. And over his career, he has worked at many different institutes, including University of Michigan, Clemson, Arecibo. He was for a while at the National Science Foundation, and then currently he's at New Jersey Institute of Technology. And he's widely recognized as an expert in the Fabry-Pérot interferometer community for advancing optical techniques to measure the upper atmospheric dynamics. And I think you're the perfect person to give a guest lecture on Fabry-Pérot interferometers for the students. Okay, please.
Well, can everyone hear me all right? Can you hear me?
Yes, we can hear you.
Okay, great. Thank you so much for the honor of this invitation to do this lecture. I had fun putting it together and very much to walk down memory lane in the sense of looking back over all the work that went into the development that took place in the past 5, 6 decades since I started this work. Let's see, how do I advance the slide?
Is it, I guess maybe your arrow keys left and right, but there was also an arrow, or maybe you click.
I'm working the arrow buttons. Okay, I try.
Yeah.
So my research is centered on the three questions: which way the wind blows, how fast, and how hot. And all this put together, it's applied to the special region of the atmosphere called the thermosphere. I thought I would start the lecture with a bit of an introduction to this area of thermospheric dynamics. So let me ask the question, so address the question, why this topic of importance to space weather? And one major region, perhaps the foremost region, is that the atmospheric drag degrades the satellite orbit, often resulting in re-entry, Starlink being one example. The mass density of the thermosphere is one of the major essential parameter of the Earth's geospace environment and the main source of atmospheric drag. Its complex behavior of the thermosphere can influence the trajectory for satellites and spacecraft, especially during geomagnetic storm period. So the question of the speed and direction of the wind is key to understanding many important aerodynamic processes. One example is the ion-neutral coupling associated with geoheating. Another is the question of the onset and development of plasma instabilities, for which the wind is very much an important ingredient in the physics of the process. And finally, the winds are very germane to the prediction of absolute density variation, which is a goal that modelers would like to achieve and had been doing so with the development of the HWM model, the horizontal wind model. Let's see. So an example is the entry of many Starlink satellites that took place during the geomagnetic storm February 3rd, some years ago. And one entry was caught on camera, and it was something that could have been avoided had the launch manager appreciated that a geomagnetic storm was ongoing and chose to delay the launch of those satellites, 50 or more on the rocket, could have been saved. But almost all of them re-entered as a result of the major enhancement of the atmospheric density in the thermosphere that came about because of the geomagnetic storm. Turned out to be very expensive indeed, multi-million dollars. So when space weather hit, the thermosphere swells up and the density increasing by 30, 40, or 50%. And satellite orbiting the Earth at speed of 20,000 miles per hour would experience such a major increase in density as if it was running up against a very strong wind. So it very much to our advantage to try to understand the behavior of the thermospheric wind in quiet and active times. And the Fabry-Pérot interferometer is a very effective instrument that helped us get the important data measurements in regard to the basic behavior of the thermospheric wind around the globe. So this shows the abstract for the very first paper on thermospheric wind during geomagnetic storm by Paul Hayes and Ray Roble. And the result of that work, which ironically was obtained on Halloween night in 1968, as I recall, the result of that work showed that the meridional wind might be as much as 300 meters per second to the south as a result of the geomagnetic storm activity. So it was a result of that Paul Hayes decided to take the trailer that represented the home for the Fabry-Pérot and the instrument itself up to Alaska, where it was installed at the location known as Exodome, overlooking the town of Fairbanks, Alaska. And I helped him do all this, and then I operated this trailer for 2 winters. And I tell you, it was really very cold in those days, minus 40, minus 50. That's quite an experience for someone that grew up in the South. So the topic for the lecture today will be to cover the basis for the thermosphere dynamic discussion, to look at the question of the ion neutral coupling and momentum balance equation, which is how the role of the thermospheric wind comes into play, and then discuss the instrument itself in terms of the details of the object and how it can be used to measure Doppler shift and Doppler broadening, from which we get temperature. And then talk about some results that feature the application of the Fabry-Pérot from recent observation at various places around the globe. So let me show this montage of photograph of many observatories around the world, which represent places where the Fabry-Pérot has been used to observe the upper atmosphere winds. And some of these, the location you may recognize as being associated with Norway, the Alomar LiDAR Observatory being one place. The feature in the center is the Antarctica dome. You might see Arecibo in the bottom part of that graph. Then lower right is the Davis Science Center in Poca Flat, Alaska. And there's the Sonderstrom radar, which no longer exists. So the thermosphere is defined as the region where the composition of the atmosphere is no longer a result of convective turbulent mixing. Above this boundary, diffusive equilibrium sets in, which means that the atmosphere composition depends on the altitude and the scale height. And this is said to be a state of hydrostatic equilibrium. And you see the temperature profile behavior in the graphic to the right, showing the difference between solar minimum and solar maximum, for which the temperature varies from a minimum of maybe 700 degrees to a maximum of about 1200 to 1400 degrees near solar maximum. It is this particular temperature that the Fabry-Pérot is able to measure, because the emission of the 630 night glow takes place at around 250 kilometers. So the temperature there is very close to that being of the exabase temperature at 400 to 500 kilometers. And this shows a simplified view of the ionosphere thermosphere system, where the magnetospheric electric field imposed by the solar wind onto the polar region of the Earth's geospace system drives the E cross B drift that governs the behavior of plasma at high latitudes during the night, in which you see within the aurora zone, the polar region, plasma drift toward the sun, and across the polar cap, past plasma drift away from the sun. So this shows how the geospace system is quite complicated, with the ionosphere, the ionospheric dynamo, and the thermospheric structure, and so forth, and photochemistry entering in as part of the big picture. The air glow structure is presented here. You have in the upper region of the atmosphere the production of UV air glow, and around 250 kilometers you have the red line emission by atomic oxygen at 630. And then below that, around 100 kilometers, you have the production of the green line emission of the night glow. We typically use the red line for Fabry-Pérot observation, and occasionally the O+ emission at 732 nanometers. The green line night glow is difficult to work with because it's so much a part of the complex mesosphere dynamic that involves a significant vertical gradient. So it's not clear exactly what you're measuring with the green line Fabry-Pérot observation of Doppler shift. I've been a skeptic of green line observation, but several of my colleagues have been trying to work with it. And it's clear that the green line observation tends to be considerably less than the speed of the mesosphere associated with chemical releases, such as the TMA of Professor Miguel Larson. So this illustrates the atomic energy levels associated with oxygen. So you see there the singlet S, which is around 4 electron volts. And then there's the singlet D, around 2 electron volts. And then the The transition from the single D to the triple P is what gives rise to the 630 emission. And that's a forbidden transition. So that's why the lifetime of the single D is as long as about 2 minutes, 120 seconds or so. There's the transition in the UV, 2958 antrim, but that transition is not very often used because it's so difficult to access the transition. The atmosphere ozone layer tend to block the transmission of the light at that particular wavelength, so it's not used in Fabry-Pérot work. So to understand thermosphere dynamics, there are several terms that need to be familiar with. Pressure gradient is obvious enough, and thermospheric winds tend to blow across the isobar contours. In other words, in the direction of the pressure gradient. This is unlike the surface weather where you tend to have a flow around a low or around a high. In the thermosphere, the flow goes across the isobar contour following the local pressure gradient. Then you have the ion drag, frictional heating, and this is a result of the collision between the neutral constituent and the plasma constituent. The Coriolis force is important for high latitudes, but not for low latitudes. During the course of a geomagnetic storm, you will have geoheating taking place in the polar region, and this results in expansion and upwelling of air in the polar region. So you have significant vertical winds. And this illustrates the distribution of geoheating associated with the polar region. And the graphic A illustrates the latitudinal behavior. The graphic B shows how the altitude profile of the geoheating shows the maximization of geoheating at around 110 to 120 kilometers. And geoheating becomes very important in the course of a geomagnetic storm as a result of the large amplitude of the electric field imposed upon the polar region from the magnetosphere. So this illustrates the ion-neutral coupling that take place as a result of the ion drag. This is the momentum balance equation interpreted in terms of temperatures. So you see the relationship between the ion temperature and the neutral temperature, as well as the neutral wind and the ion drift. The time scale for ion to respond to the flow of air driven by a pressure gradient from day to night, say, will tend to be a few seconds to a few tenths of seconds, depending on the plasma density. The time scale for neutral to respond to frictional heating pretty much related to the collision frequency. The ion is more apt to respond quickly to changes in the electric field. The neutral wind tends to lag behind with a response time of a few tens of minutes to quite a bit longer if the plasma density is low. This illustrates the distribution of the winds at high latitude. Generally speaking, you have flow toward the sun within the aurora region that's driven by plasma convection. You have very high winds across the polar cap away from the sun. And again, this is driven by the polar cap electric field. So the energy flow during the storm is partitioned between particle precipitation and the E cross B drift, electromagnetic energy. And there it's geoheating it's the major fraction of the electromagnetic energy deposited during the storm. So you see the distribution of the various mechanisms associated with the dissipation of energy associated with the influx of particles from the sun as a result of a geomagnetic storm. Switching now to the Fabry-Pérot instrument part of the talk, as I've been saying, the Fabry-Pérot is an instrument that may use the 630 emission to observe winds and temperature using a number of assumptions, all of which are quite reasonable. So why observe the dynamics of the Earth with the Fabry-Pérot? As I've been saying, to understand the chemical and physical processes going on in the polar region, and to monitor temporal and spatial changes due to the geomagnetic storm or CME event, and to enable space weather forecasting by getting real-time data, to determine climatology that are then used by empirical models, such as the horizontal wind model that's managed by NRL. So Fabry and Pérot, who are these guys associated with the Fabry-Pérot instrument? These were two French physicists that invented the concept of the interferometer and did extensive work with the instrument in the period of the late 19th century. Fabry was the theorist that thought of the instrumental concept, which featured multiple beam interferometry. And Pérot was the experimentalist of the team, and he was very mechanically talented. This is the Fabry-Pérot that he built. It's hard to see the details, but they're quite a capable Eidolon that he built here. The source that I've been talking about, the 630 emission, is generated by a dissociated recombination of O2 plus or NO plus within the region of 220 to 280 kilometers, with the peak of around 240 to 50 kilometers. These molecular ions are formed by charge exchange of O plus with O2 or N2. You might wonder, why is it that dissociative recombination is the major mechanism for the production of the O single D? Why not just simply O plus combining with electron, O plus plus E giving you O, with the O atom being excited? And the reason is it's really related to quantum mechanics. When you have a collision of O plus with an electron, you do not have a third body to carry away the excess momentum associated with the union of the electron with the O plus ion. So the rate constant for this reaction is very slow, whereas the molecular ion is more able to break up into oxygen fragments because there's a third body that's there to carry away excess momentum in the interaction. So a quick summary of the Fabry-Pérot is a high-resolution interferometer that's used to observe the line shape of the 630 emission, which is very narrow. So that's why a high-resolution instrument is required to be able to observe the line shape and to measure the Doppler shift of the line shape. The optical principle of the Fabry-Pérot is based on multiple beam interferometry. So it's different from the microzone interferometer, which is a double beam instrument. So you just have two beams combining for a microton, whereas with the Fabry-Pérot representing multiple reflection between two mirrors that are parallel to one another, you have multiple reflection back and forth, so you end up having multiple beam interference taking place. So the Doppler line center of this spectral profile gives a measure of the line of sight Doppler shift, but relative to a zero-wind Doppler reference. For a radar instrument, to measure Doppler shift, you usually have a local oscillator that gives you the Doppler zero shift reference. We don't have anything like that in the Fabry-Pérot world. We do have a frequency stabilized laser at 632.8 nanometers, but it's about 28 nanometers away from the 630 emission. And it's close enough for the purpose of calibration, but it doesn't give us a good measure of the zero wind Doppler reference that we really would like to have. The full width of the Doppler broadening gives us a measure of the temperature. We also have optical emission from or as a result of particle impact. Here's an illustration of an etalon with two mirror surfaces that you see here. You superimpose one plate on top of the other, and you have a gap between the two plates. The plates are made to be very parallel as possible, and that enables the light beam to reflect back and forth. The reflectivity of the mirror surface is a very important parameter. Typically, it's 80%. This means that for each encounter of light with the surface, with the mirror surface, 80% of the light is reflected. 20% of the light is transmitted through the etalon glass surface into the backside. I'll show you an optical diagram of the Fabry-Pérot object. You expect an azimuthal symmetry to the interference pattern, and I'll tell you more about why that is so. So this shows the diagram of the multiple between the two mirror surfaces of the etalon. You see the multiple reflection taking place with reflection going off to the left and transmission of the light off to the right. They're gathered by the lens there, the objective lens, and this is what brings about the interference, because the lens combined those multiple rays, multiple beam passing through the etalon, combines the rays into a interference pattern that is formed on the surface of the screen. The Doppler shift is measured by the expansion or contraction of the circular ring pattern. The temperature is determined from the broadening of the spectral profile relative to what you would measure for a zero temperature profile. And that is the purpose of the spectral, the purpose of the frequency stabilized helium neon laser that we used at the 632.8 nanometers. This illustrates an etalon, and you see the gap between the two mirror surfaces. The number of rings that you see in the interference pattern depends on the specification of the gap spacing and the focal length of the lens. Those are two very important parameters. The larger the spacer, the more the rings you will have. The shorter the focal length, the more rings you will have. So being able to make a very fast instrument in terms of the optic. It allows you to expand the field of view that the Fabry-Pérot can observe looking out onto the sky. Typically, one order is about 0.1 degree. So if you have 10 orders in the ring pattern, you're covering a total angular extent of the sky of about 1 degree. So how can you get a ring pattern? There are three ways. Then the phase of the ring pattern, the position of an order at depends on the various parameters you see in this formula here. Mu is the index of refraction, and that is pressure dependent. So changing the pressure within the etalon allows you to change the phase. And so you are able to scan the source emission to get a full spectral profile of the source that emitted by the sky. T is the thickness of the gap. So if you change T as you could by using a piezoelectric spacer, then you would also be able to change the order of interference over a full free spectral range, which is typically 0.02 nanometers for a 1 centimeter gap for the 630 emission. Then finally, if you change the angle of the light coming into the etalon, namely change theta, then you can image the sky and produce a ring pattern as a result of the illumination. And so you take a picture. And this is how it is that so much of a change has happened to the Fabry-Pérot, because the introduction of the digital camera has improved the sensitivity of the Fabry-Pérot by almost 3 orders of magnitude. This phase relation shows the azimuthal symmetry of the interference pattern, because there's no dependence on the angular phi, the angular in the rotational direction. The only angular dependence is relative to the optical axis, namely that angle given by theta. So the spectral profile is shown here. This is including the broadening associated with the source having a temperature. So what you see here is the convolution of the spectral profile associated with the source, namely a Gaussian distribution of atoms moving toward you or moving away from you, or maybe moving across your line of sight. So this broadening is relative to the instrument function, which is not shown here, but I will show you in a bit. So you look at the Doppler line center, namely the peak of the spectral profile, and you look for the shift of that peak position relative to a position that's known to be associated with the zero Doppler shift. And this is where it becomes a little bit awkward to talk about the Fabry-Pérot calibration, because we don't have a local oscillator. We depend upon the idea that the vertical winds of the thermosphere tend to be close to zero for the most part throughout the night, especially for very quiet times. So by looking up during the night on occasion, it's possible then to get a pretty good idea of where the zero Doppler shift reference might be within a few meters per second. But this is always the weak point, and it's always the holy grail for Fabry-Pérot experimentalists to think of a way of generating a local oscillator that could be used for zero Doppler shift calibration for the Fabry-Pérot. The area under the profile is proportional to the source intensity. So if it's very bright, then you will get quite a bit more signal across the spectral profile, and that would improve your ratio of signal noise quite a bit. So the 630 emission comes from the slow release of the energy built up by solar photoionization during the day. And then during the night, the recombination of O2 plus with electron produces the O single D state. There are three particular lines associated with the relaxation of light from the O single D state. The 630, the primary state transition from the single D to the triple P 2 state, J equal 2. Another line, the 63 6.4, but it's 3 times dimmer. And it's also confused a bit by the OH emission nearby. And then there's the third transition that's at 639.2 nanometers, and it's very weak, and no one ever uses it. So the single D state can be created by a number of processes. I've already talked about the dominant source, the dissociative recombination of O2 plus ion. You also have the impact of the electron from the high energy tail of the thermal distribution, or from aurora particles coming in, whether electrons or photons. And then you also have the dissociative recombination of NO plus that form as a result of charge exchange of O plus with N2. This is one of the early examples of measuring the Meridiana wind that I showed you earlier. And you see that you have to look in different directions in order to get a measure of the Meridiana wind component or the zonal wind component, as the case might be. In this case, looking to the north, it was much brighter than looking to the south. And the integration period was 2 seconds per data point that you see here. This set of profiles took about almost an hour. Went from 240 to 325. For the situation of an aurora, nowadays we would just need 1 minute, 60 seconds to get data that was quite a bit more precise than what you're capable of getting from these measurements. What you see here are 2 orders that are covered by the pressure scan across a free spectral range of about 1.7 psi. So moving forward at least 40 years, imaging Fabry-Pérot is so much more sensitive nowadays than the scanning Fabry-Pérot of 40 years ago. And here's a comparison. And I'll come back to this table with a more developed table, giving you an updated version. But for a typical Fabry-Pérot using imaging, a digital camera, you might get 10 orders. So that's an increase of a factor of 10, because each order is independent of the others. So the energy of one order is the same as the energy of each of the other 9 orders. The detector quantum efficiency for a digital camera that's very quiet is really big, 90%. that means that almost every photon is counted. But in the early days, one used a photo multiplier, and the quantum efficiency of the surface detector was 10%. So there you have a factor of 9. Then the Edelon aperture might be very much the same, 6 inches across, 15 centimeters. But for a scanning instrument, you only observe an order about 10% of the time. So there you have a factor of 10, because with a camera, you're observing the whole order of the ring pattern at the same time. Whereas with a scanning Fabry-Pérot, whether pressure scanning or piezoelectric scanning, you have to use an aperture. That means that 90% of the light from the peak of the order will be excluded. And this is a typical Fabry-Pérot setup in the laboratory. There's a scattering chamber where we bring in the light from the frequency stabilized laser that we use for calibration. And then the scattering take the light up past the 2 mirrors back into the instrument, and then pass through the interference filter there that isolates the 630 emission relative to all the other night glow emission. Then the light passed through the Edelon chamber, and where multiple interference is taking place. And then it's focused by the objective lens onto the front surface of the digital camera, and that produced the ring pattern that's associated with the Fabry-Pérot interference pattern. So here's an example of a calibration with the laser, and you see the various rings there. This is a function of the distance from the center of the ring pattern. In angular space, it would be theta squared, but in the detector space, it would be simply the distance here. What one does to analyze the data is to integrate around the ring center, where you see the green plus sign in the center of the pattern is what we take to be the ring center. And we get it very close to a zero pixel displacement from the center of the detector. We're just usually off by 1 or 2 pixels. And you collect all of the light around, integrating around the ring center. So you break up the radius from the center of the chip out to the edge into annualized, maybe as many as 400 annualized, and you collect the signal from the various pixels as you go around the angular space along the ring that you see there. So to the right, you see the result of that integration. And you can also see that the spectral profile is very clean. It's not noisy at all. This is for a fairly bright laser source. This is what we see for looking at the sky. So you can see the rings are considerably broader. And then when we do the annular integration, you see the orders over there to the right. Even when the light is fairly dim, and this is just a few Raylys of 630 emission, you can still see a fairly good quality spectral profile as a result of adding the light from all of the pixels around the ring center. So the analysis of Fabry-Pérot images involve tracking the fringe phase location and spectral width, producing an estimate of the Doppler line centers and temperature. So I will discuss this a bit further. I'm going to get into the math because I thought this would be helpful to newcomers coming into the Fabry-Pérot field. There's a number of ways of coming at the analysis of these ring patterns, one-dimensional spectra. Here you see the phase relation relating x to the cosine theta. The expression to the right of it is A is the area function. And this is what I will be showing you as to how it's derived. But it represents the spectral profile of the instrument. That is the function of the reflectivity R that you see there. After you sum around the ring center to transform from 2D to 1D, you have this relationship at the bottom with the pixel count Ni being the function of the area of the etalon, the field of view omega I, the time of integration T, the quantum efficiency Qi, and the transmission of the object and the filter. Then within the integral, within the integrand, you have the Y being the instrument function. Y being the source function of the sky signal in terms of the speed of the atom moving away from you or toward you. The big phi there, function of lambda and theta I, represent the instrument function, and T represent the transmission of the filter. So this is the signal for a particular ring, annular ring around the ring center. So I'll take you through the derivation of the area function, which come from considering the multiple beam interference, as you can see in this diagram. And I'm following material that was written up by Brian Harding, the part of his PhD dissertation. So the interference pattern arises from the coherent sum of all the transmitted rays. So there you have the electric field total being the sum of the contribution to the electric field as a result of the multiple beams that are associated with the reflection back and forth between the inner surfaces of the two mirrors of the etalon. And what you see is that there's an infinite series there that can be re-expressed in terms of the fraction 1 over 1 minus x. So this is where the area function is derived. Another way of thinking about the area function is that it's a Bessel function, a zero-order Bessel function. I'm not associated with that nomenclature, familiar with that nomenclature, but I thought I mentioned it in passing. To derive the intensity, you want to take the square of this function, and that's shown here to the right. And this is what leads into what we call the area function, the square of the electric field total added up over all of those contributions. So the approach that Paul Hayes took in analyzing the Fabry-Pérot fringes, and the approach that I followed is one involving the analysis of the instrument function by Fourier series. So he used a Fourier series expansion to represent the instrument function. And when you evaluate that integral for big phi with the Gaussian function that's associated with the thermal distribution of the moving atoms in the source night glow region, you can evaluate the integral, as you can see here, coming up with this formula at the very bottom that involves the integration, the sum over the various Fourier coefficients. So you have four unknown, the background U1, U2 associated with the intensity, the area, U3, the quantity associated with the Doppler shift, and U4, the quantity associated with the temperature. So you evaluate this in a nonlinear least square fashion, making use of Levenberg Marquardt approach. And this is described in the paper by Hayes and Roble in 1971. So here's a summary of the process that described with those formulas. There's the ring pattern. This is the angular integration. Then you do the Fourier analysis of each one of those fringes, and you generate the Fourier coefficient that you used in that bottom formula in the previous slide. And then you apply this to, once you have the Fourier coefficient, you apply this to the sky image, do the angular integration again, but then you apply the nonlinear least square processing to get a profile fit to the data that you see in this example. So this is an approach that works, but it's quite complicated and cumbersome because of the multiple coefficients of the Fourier series used to represent the instrument function. Brian Harding introduced an alternative approach that sum up right here. And this is referred to as the blurring model. And it's much less demanding of computing resources and is simpler to follow. There, the top line is the Fredholm integral that I showed you before. The B function there is the blurring model, but also represents the Gaussian distribution of thermal atoms. The A function that you see there is the modified area function, where the modification is the numerator, in which the two additional terms, I1 and I2, and these are introduced in order to allow for the reduction of the signal associated with optical vignetting of Fabry-Pérot optics. So if you were to look at the this ring pattern associated with the laser profile, you see how the profile of the fringes broaden somewhat as you go from left to right, and the peak shortened a bit from left to right for each one of those peaks. The I1 and I2 in that blurry model expression is intended to allow for that reduction of the peak height, as well as a slight increase in the full width half maximum. And then you have the slight modification of the sigma in order to allow for the blurring of signal by one pixel to be associated with the signal of several pixels knit together, so to speak. And the analysis has taken place as a result of the nonlinear least square approach. And it worked reasonably well, quite well. As you can see here, the comparison of the model fit with the data for the sky shows very little in way of residual. So this approach worked quite well, and it's quite a bit less cumbersome than the Fourier analysis approach that I talked about just before. So most everyone in the imaging Fabry-Pérot field makes use of the hiding data analysis blurring model. So what we get from the data analysis, we get from the spectral width, we get the temperature, but we assume a Gaussian distribution for the line shape for the source. And this is believed to be a very good assumption. There's no evidence for any departure from a Gaussian distribution for the region of 250 kilometers to 300 kilometers. The Doppler center, line center gives us the Doppler shift, but we have to make the assumption that we can do a pretty good job of deriving the Doppler reference by looking at the zenith, as I've discussed before. From the line shape area, we get the intensity, but it's generally uncalibrated. But we could calibrate the Fabry-Pérot intensity response by comparing with a simultaneous measurement taken by an imaging off-sky system that calibrated. So having these data products for many nights of observation allowed the development of climatology on a monthly or seasonal basis for the zonal wind U, the Meridiana wind B, the vertical wind W, and for temperature. So indirect data product will be measurement of the gradient for zonal and Meridiana wind, and we do see gradient. And it has been possible to make use of a very good sensitive Fabry-Pérot to observe vertical winds, and we do see variation with perhaps 10 to minute periodicity. So this illustrates the first set of measurements that I took way back when in the early days. This represents the quality of the measurement that we got with scanning Fabry-Pérot, and the analysis to the right shows that we saw the result of the plasma convection producing by ion drag, the neutral flow toward the sun, followed by the Meridiana wind to the south. And at the very bottom, you see a series of arrows that represent the wind pattern. Westward winds against the pressure gradient associated with day to night flow, and then the Meridiana wind to the south that was considered to be a result of the heating of the aurora zone by the influx of aurora particles. And this is a distribution showing the location of various Fabry-Pérots around the world in 2014. Some of these Fabry-Pérots no longer exist. For example, the one in southern Peru, Arequipa, Peru, is no longer in place. The one at Arecibo is no longer there, though there's one in Fabry-Pérot at Culebra. So an issue not appreciated in discussing neutral wind measurement obtained with Fabry-Pérot is that a single station Fabry-Pérot cannot measure a single neutral wind vector U. The observations in the north, south, east, and west and zonal zenith direction are all line of sight components of separate wind vectors, one for each of those directions. The north and south direction are separated by 500 kilometers because of the height being at 250 kilometers. And usually we use a zenith angle of 45 degrees. So the separation is about 500 kilometers. And generally speaking, the wind vectors are different, even for a separation of 500 kilometers. This issue is okay for climatology purposes, but for gravity wave observations, where you'd like to have all four components of the neutral wind vector, this approach is not okay. So to measure the three components of a neutral wind vector, you need to have common volume measurement. Three Fabry-Pérots observing the same volume of space to measure line of sight wind component. And Mark Conde has been using this approach to do his work with his SDI Fabry-Pérot. I don't have time to talk about that particular instrument, but it's the Fabry-Pérot in principle, but the approach is quite different from the imaging Fabry-Pérot using the digital camera. So just wanted to illustrate that the comparison of satellite observations such as that obtained by ONCON with the ground-based measurements show good agreement, providing confidence in the Fabry-Pérot accuracy. This shows the vertical profile of the wind obtained by ICON between 200 and 300 kilometers for two locations, Urbana, Illinois, and Morocco. And the data point for the two ground-based Fabry-Pérot is bang on in good agreement with the ICON observation, mighty observation. This shows the comparison of the satellite measurements of the zonal and meridional wind with the ground-based measurement. And again, quite good agreement. So over the years, there've been quite a few separate Fabry-Pérots that I've been involved in setting up. And the issue is that in my field, in neuronomy, you have to go where the science is. And if you're going to make the measurement from the ground, you have to be willing to travel to get to wherever it is that you want to be making measurements. So Arequipa, Peru was something I started in 1983. And then Calgary, I started that in the mid 1980s. Sandstrom, I did in the early 80s as well. And then with Tim Colleen and Herb Carlson's support, we put in a Fabry-Pérot at the Thule Air Base in Greenland. And there's other Fabry-Pérot observatories, Brazil, Ethiopia, Argentina, Jenny-Jump, Svalbard. It's been all great fun, and I've enjoyed working with many colleagues all around the world associated with these observatories. I wanted to show you an example of the application of the Fabry-Pérot to measure winds and temperature over a long period of time. This is from the work that Jonathan Makela and I did in Brazil. Here we have the progression of the solar flux from January 2010 to July of 2012. So there's a major increase in the solar activity, and the observation that we obtained over the various months are shown to the right for the 12 months of the year. The big difference between the measurement that I did at Arequipa, which was applied for the mid-90s, was that the Arequipa weather was bad for the local summer. It was only during the local winter that I was able to get good results. Here in Brazil, we were able to get good quality results for all months of the year. So we really, for the first time, were able to see the climatology of the winds for an equatorial region location. This was about 5 degrees away from the geomagnetic equator. And you can see how the temperature increased as you go from solar minimum to solar maximum. The orange is the solar minimum, green is slightly later, 2011, and the violet purple is for 2012. And this illustrates the zonal and meridional winds over the same months. One takeaway observation is that the thermospheric wind is quite variable in direction and amplitude speed from night to night or month to month. Typically, though, you see fast eastward winds, the zonal wind during the evening hours, and that would be followed by meridional flow toward the polar region during the post-midnight hours. And for the case of a geomagnetic storm, this is from a Fabry-Pérot in upstate North Carolina, just a few miles from Clemson, and from Illinois, Urbana. And we had a major geomagnetic storm in the 14th of November in 2012. And you can see how it got quite a bit hotter as a result of the storm. What I'm showing here is the meridional wind in the lower left and the zonal wind to the lower right. And you can see how the nominal eastward wind during quiet time is replaced by westward wind during the active storm time. And then the upper panel on the right shows the temperature behavior over the course of one night. We had clear skies for 3 nights in a row, and you can see that the storm became quite a bit hotter. The thermosphere temperature became quite a bit hotter during the peak of the storm activity. This is another example showing the temperature for the various directions. And in this case, the lower panel on the left shows how, looking to the north, you could see temperature at about 100 to 150 K hotter. Then you have the temperatures for the other nights shown for the two observatories, Perry and Urbana, Illinois. So moving forward, I will talk to you about a more modern Doppler imager system that we call HODI, hot oxygen Doppler imager, because we wanted to observe the Doppler shift associated with the O+ ion using the 732 emission of O+. So the characteristic of the Jenny jump Fabry-Pérot is 15 centimeter. The MACV instrument is 20 centimeter, and I'll show you that at the very end. Then a lens assembly that flattened the focal plane so the whole field is in focus. Very good quality, low noise CCD camera, double active sky scanner, 2 filters, capability 630 and 732, using a 4-position filter wheel. This is the Jenny Jump Observatory in upstate New Jersey. That trailer is where HODI was located. And this is the sky scanner. And this is the instrument itself. The 15 centimeter headline is in that upper black chamber. The camera is at the very bottom, and the black area in between is the achromatic lens assembly. And this shows the filter wheel assembly as well. The headline is missing in this picture to the right. What I learned by developing this instrument was that the achromatic objective lens that I thought I could buy for $1,000 wouldn't work because the image is out of focus in the corner of the focal plane. And so to work at shorter focal length so I can get the 10 rings meant that I really need to deal with this problem of having a curved focal plane superimposed upon the flat detector surface. So it's possible to design an objective lens assembly where a corrector lens is added to produce an image in a focal plane that would be flat. So this is illustrated with the object here. And so I was quite excited to see this ring pattern sky for Hody in Jenny Jump in 2022. And this shows the angular integration that result in the very good quality orders. And this shows that the Harding model worked pretty well in making use of a laser interferogram to fit the data of the sky. And this shows some result, vertical direction obtained by using Hody. We have 5 active nights, and that illustrate the various responses of the vertical wind on the far left, temperatures in the middle, and then the residuals. By taking away the long-term variation, we're looking at the temperature and vertical wind residuals. And the oscillation that you see, we consider to be real and relate to gravity wave activity passing through the thermosphere region. So this is the last night of observation before we took Hody to Svalbard, where we set it up, and we were quite successful in observing plasma convection with the 732 emission. So this shows the zonal direction, and this shows the vertical wind activity with the temperature behavior as well. So there's one last instrument I'll talk about before concluding this lecture. I was able to get a funding by NSF to buy from Keogh Scientific a Fabry-Pérot that would be state of the art in the sense of being able to observe helium at 1083 nanometers. I want to observe, if I can, the difference between the thermosphere winds at 250 kilometers and the exosphere winds at 500 kilometers, which I can measure with the observation of helium. This illustrates how much more sensitive MATFE would be compared with the pressure scanning Fabry-Pérot of my Michigan days. It's about 3 orders to magnitude, 7290. If you follow through the Edelon aperture, the fraction of order, the detector quantum efficiency, etc. But for MATFE, we get 27 orders rather than just 10. So the major differences, the aperture is bigger, so we have twice as much area, and the detector is bigger, so we can observe out to 5 degree angular extent instead of about 2.5 degrees. And the reason for wanting to observe helium is illustrated here. The Fabry-Pérot shows the winds that are greater by a factor of 2 compared with champ winds for the midnight period. This is a graphic taken from a paper by Ansuya Arilaya, and which she demonstrated on a statistical basis that there's a discrepancy between the Fabry-Pérot winds and the champ wind seen at midnight. The champ winds are at 400 kilometers. The Fabry-Pérot winds are lower at 250 kilometers. So it looked as if there's a difference in the wind speed between the two altitude regions. This illustrates the 20 centimeter plate compared with the 15 centimeter diameter plate. And Terry is the person that makes this all possible. And this illustrates the development of a Etlon surface, which has to be very, very flat. And this goes on all day. And here are some images of the MATFI instrument. So it's all ready to go. And this is the result of a laser calibration in the laboratory. And we're getting about 29 rings. And you can see that we are able to do the angular integration. So this is going to be quite a bit more sensitive instrument to observe gravity wave activity in the thermosphere region. So that's it. Thank you. How do I?
Thank you. Thank you, John. Are there any questions from the audience? Well, I have a few questions, while other people may think of questions. So you mentioned
Sure.
that increasing the number of orders for Fabry-Pérot interferometer would increase the sensitivity, but when I look at your the fringes, the intensity of the fringes does roll off. So I'm guessing that you cannot go up to infinite number of orders because you won't have any more light at the end. How far do you think you can go? What's the highest order of magnitude, the highest order fringe that you still think that you can get useful information out of? And you mentioned that
That's a
the
good
sensitivity is 27 times higher for max FPI. And
each order is about a tenth of a degree. And so 29 orders represented about 3 degrees, plus minus 3 degrees. So a full angle of about 5 to 6 degrees. We can't go much beyond this angular extent. So I would expect that there's a limitation that will come in because you have what we call walk off, in that the rays bouncing back and forth between the two mirror surfaces will not continue to bounce back and forth, but walk off to the edge. So you have leakage out around the perimeter of the Enlon plate.
Hmm.
And that was something that I didn't know until we got the first laser cal, just how good will the fringes be out this far out to the edge. And to my surprise, it looked to be pretty good. There is a drop off, yes, but that's more likely a result of vignetting of the Etlon object, similar to what we see for Hodi or for any of the other Fabry-Pérots that we put out in the field around the world.
Okay, thanks. I had another question. It was related to the storm time response. Can you show the slide where you had the storm response of the temperatures and the winds? It was a really neat one. Yeah, like that one. So I guess the storm response here is labeled as 13th of November, but it's because it starts right before midnight. Um, and you can see a sort of a equatorward surge, I guess, of the meridional wind
Yeah,
to
yeah.
TC, and then you can also see the temperature rising at 4. But in this temperature, I noticed that this oscillation. What would you attribute the oscillation of the this green scatter plots? Is that the instrumental effect, or is that some kind of a wave activity in the neutral temperatures?
Which oscillation are you
On the
making?
top right plot, in the neutral temperatures.
Uh, well, you do expect traveling atmospheric disturbances to take place. Uh, we're talking about mid-latitude observation. This location for Perry, it's right around 35 degrees north. So TADs generated in the Aurora region would be propagating down to the south because they're aligned with the Aurora oval. So it would be very much of a surprise if we didn't see evidence for these TADs. There's also associated TIDs, and but that wouldn't show up in the Fabry-Pérot measurement. With the development of the GNSS network, GPS network that we have in the continental US, it would be possible to compare the scintillation measurements seen in those GPS results with these Fabry-Pérot measurements to look for correlation between the oscillation of the plasma and the fluctuation of the neutral wind. I didn't want to take the time to show you the result from Argentina, but we have seen a series of vertical wind oscillation that seems to be associated with a pattern of TIDs moving to the southwest. And we make the point that the explanation for the vertical wind oscillation come from the flow of surface winds across the Andes, generating orographic waves that are propagated upward into the region of the thermosphere. And we show theoretical results that were generated by Dave Fritz and his colleague that illustrate these oscillations. And the vertical winds look to be fairly large.
Okay, thanks. Are there
I
any?
think this is a future direction for the Fabry-Pérot to be of studying the fluctuation on a short time scale basis.
Yeah. Then I had one more question. You mentioned that the calibration is a challenge. And you use I guess I understood you use two different types of calibration principles, either a laser, which is a couple of nanometers off, or you assume that the average vertical wind is 0. Which one do you use more often, and what are the pros and cons of both of these calibration approaches?
Well, what we're trying to do is to measure the displacement of the laser Doppler line center relative to the Doppler line center of the zenith. But this displacement might be 300, 400, 500 meters per second. A full free spectral range for a 1 centimeter spacer is about 10,000 meters per second. The phase difference between the laser peak and the 630 peak might be 2,000 meters per second or something like that. whatever it is, we argued that it's constant. So if you measure the laser, then you apply that offset, you get the Doppler line center for zero Doppler shift for the 630 emission. We avoid twilight because we have learned that there is an artifact of an artificial Doppler shift associated with twilight. So we take the genus measurement from, say, 9 p.m. to 4 a.m., the 7 hours associated with the midnight period, and we look at all the differences of the genus relative to the laser Doppler line centers, and we average those differences. And we're making the assumption that the displacement of the laser peak to the sky peak is a constant. So if we measure where the laser is, we know where the Doppler line center is for the sky. We think that the Doppler zero shift reference that we measured this way is accurate to within a few meters per second. It could be off by 5 meters per second, or at the very worst, 10 meters per second. But we have no alternative. That's the best we can do at the moment. There have been an effort to make a lamp that could even generate 630 emission of oxygen in the laboratory, but it's not very successful in the sense of providing a lamp that could be used in the field. You can generate O emission in the laboratory, but you need a room full of equipment to make it happen.
Okay, are there any other questions about Fabry-Pérot interferometers? I think there's a room full of silence. I think that's it. That's it then. Thank you very much, John.
You're very welcome, and I had a great time putting it
Yeah.
together, but you still owe me a beer.
Yeah, next time when I see you, I will buy you a beer.
Great. Thank you.
I think I now understand a little bit more about how Fabry-Pérot interferometers work and how much work actually goes behind each one of these measurement points. It's
Yeah. I'll send you a PDF version of the talk
okay.
later.
Thank you and have a nice rest of the day. Thank you everyone for participating. Bye.
Thank you very much. Bye-bye.
Bye-bye.